Hi everybody, hope your day is going well. Just kind of a heads up, the next couple of lessons that we're doing, including today's lesson, are some of the most important lessons we will do all year in AP Calculus. We are going to use this information not only in this next couple of sections, but we're going to use this the rest of the year. We're going to use this in Chapter 4, we're going to use this in Chapter 5, etc. This is a heavily tested area on the AP test, and they have a lot of justifications based upon this where you got to write out and explain what's going on. Again, highly recommend that when we go through this, you actually learn it the way that it's presented and not try to come up with your own method for dealing with this, because we are going to apply this information in many, many different ways, and you don't want to have to learn it 6 different ways when you can learn it just one way, the way it's being presented. And so our essential standard is I understand and can find critical points. I understand, can find, and can justify increasing, decreasing, and constant behavior. I understand, can find, and can justify an extrema, giving a local argument for a relative extrema and a global argument for an absolute extrema. A function is considered increasing on an interval, a to b, if the derivative of the function is greater than 0 for all x in the interval. A function is decreasing on an interval if the derivative is less than 0 for all x in the interval. And remember, a derivative is a rate of change. And so if the rate of change is positive, that function is increasing. If the rate of change is negative, that function is decreasing. Finally, and this doesn't show up a whole lot in AP Calc, but again, a function is constant on an interval if the derivative is equal to 0 for all x in the interval. And we have a nice little diagram over there where over here it's increasing, over here it's increasing, over here it's decreasing, and over here it's constant. And when we're talking about an interval, we're talking about x values. We're talking about the x values over here to here. We're talking about the x values here to here. We're talking about the x values there to there. And we're talking about the x values there to there. We've done this increasing, decreasing, and constant in pre-cal where you guys looked at graphs. Calculus is going to add all the analytic stuff to this. One final important note, if the derivative is equal to 0 for a finite number of x values, it is still increasing, decreasing on that interval. For instance, the function f of x equals x cubed is increasing for all numbers, even though if we take the derivative of this, f prime of x, we're going to get this 3x squared. And notice that this is going to equal 0 when x is equal to 0. This particular function happens to be increasing for all values, including the value x equals 0. Because if we were to analyze this derivative, it's positive on both sides. And because it's positive on both sides, this finite point over here doesn't change that increasing or decreasing nature. The only time that you're going to get constant is it has to be equal to 0 for a interval of values. If it's just equal to 0 for a single finite value or multiple finite values, it's still going to be increasing on that interval. And again, the best way to think about this is the pre-cal definition of increasing, decreasing. Increasing requires, when you're going to do your graph, it requires a bigger y value on the right and requires a smaller y value on the left. If you were to plug in 0 into f of x cubed, and then you were to go a small amount to the right or a small amount to the left, the values are bigger on the right and they're small on the left, which means that it's going to be increasing at 0. A function is strictly monotonic if it is only increasing or only decreasing on an interval. They want us to find the intervals in which the function is increasing, and they want us to give a reason for your answer. And this over here is basically how every single question on the AP test goes in the free response section. They're going to ask you to justify your answer. They're going to ask you to put words to what you answered. If you actually understand what you're doing, putting words to this is very, very easy and very, very straightforward. So again, try to focus on understanding, and then the words will naturally follow from that. We know that a function is increasing if its derivative is positive. And so we're going to find the intervals on which the derivative of the function is positive. And so we have the function f of x. The derivative for f is going to be f prime. This is going to be negative 4x cubed plus 12x squared. We're going to find out when it's ever equal to 0 or when it's undefined. It's never undefined, but it is equal to 0 at some values. There is a negative 4x squared in common. There is going to be an x minus 3 that's going to be left over. This is going to give us x is equal to 0 or x is equal to 3. If I try to analyze this derivative, and again I'm analyzing f prime, I have two critical points. My critical points are 0 and 3. And then I got to figure out what happens on each of these intervals. And so I'm going to go look and try to analyze this particular expression, my derivative, and see if it's positive or negative on the intervals. Exactly the same process we did in Algebra 2 as well as in Pre-Cal. And so if you plug in a number like negative 1, the negative 4x squared will be a negative number. The negative 1 minus 3 will also be a negative number. And this over here is going to be positive. If you plug in a number between 0 and 3, like 1, that negative 4x squared is going to be, again, negative. That 1 minus 3, again, is going to be negative, and negative times negative is positive. And then finally, if you plug in a number like 4 that's bigger than 3, the negative 4x squared will be negative, but the 4 minus 3 will be positive, and negative times positive is going to be negative. They want us to give the intervals on which this function is increasing, and so this particular function is increasing all the way from negative infinity all the way to 3. Just because it was equal to 0 at this particular point doesn't change that it was still increasing at that particular point 0. But we just get one interval between negative infinity and positive 3. We want us to give a reason for our answer, and we're going to say something as follows. On this interval, f prime of x is greater than 0, except at the finite point x equal to 0, where f prime of x is equal to 0. But that over there is our reason for our answer. Basically, is the derivative is positive for the function of interest on this particular interval. Your guys' turn. Try the next one. Welcome back. They're asking us about increasing, decreasing, increasing, decreasing, decreasing. Those are all first derivative items, and so I need to go and find my derivative. And so if I go and find my derivative, f prime of x is going to equal this 3x squared plus 12. This over here is going to be greater than 0 for all x. I don't have any numbers where this is equal to 0. 3x squared plus 12 is always at least 12. My derivative is always positive. And so this particular function is going to be increasing for all x. The next one, they want us to find the intervals on which the function is decreasing, and they want us to give a reason for our answer. And so in order to do this decreasing, this is a first derivative, we got to find out where that derivative y prime is going to be negative. And so we got to go find y prime first. This over here is going to be a product rule because I got multiplication. I got a first times a second. It is going to be the first times the derivative of the second. That requires a chain rule. 1/2 32 minus x squared to the negative 1/2 power times the derivative of what's inside, which is negative 2x, plus the second, the square root of this 32 minus x squared, times the derivative of the first. It is the first times the derivative of your second, plus your second times the derivative of the first. I got to try to simplify this because I got to find out when this is negative. The function is going to be decreasing when the derivative is negative. And so this 2 over here is going to cancel out with that 2 over there. I'm going to get this negative x squared in the numerator. I'm going to get the square root of 32 minus x squared in the denominator. For the part on the right, I'm just going to get the square root of 32 minus x squared. I got to find a common denominator so I can add my fractions together. And if you do that, you're going to get this negative x squared plus 32 minus x squared, all divided by the square root of 32 minus x squared. This over here is going to be this 32 minus 2x squared, all over the square root of 32 minus x squared. That over there is y prime, that is my derivative. One of the things I probably should did when I started this problem, but I didn't do, was to find the domain. So let's go and try to deal with that right now and find our domain. I know that whenever I have an even radical, whatever inside the radical has to be positive. So I know that the 32 minus x squared has to be greater than or equal to 0. Meaning this negative x squared is greater than or equal to negative 32, or x squared is less than or equal to 32. If we take the square root of both sides, you're basically going to get absolute value of x less than or equal to the square root of 32, which basically is going to give you this negative square root of 32 less than or equal to x less than or equal to the square root of 32. And the squares of 32 are going to be these 4 squares of 2. Okay. But that over there is my domain. Back to my derivative. Is this ever undefined? Again, we have some domain issues, the same domain that we have originally, but we also have the additional exclusions of the 2 endpoint values. If you try to plug in the square root of 32 or the negative square root of 32, you get division by 0. And so when we're trying to analyze this derivative over here, this over here is your y prime. You're going to get this negative 4 square root of 2, which is your endpoint value, and this positive 4 square root of 2, which is your other endpoint value. Does it ever equal 0? And the answer is yes. This 32 minus 2x squared equals 0. This x squared is going to equal 16, and x is going to equal plus or minus 4. So we got negative 4, and we got positive 4. And then I got to figure out what's happening on each of these intervals. So I got to go look at my derivative, and I got to analyze what's happening on each of these intervals. If you plug in a number like 0, the numerator is going to be positive, denominator is going to be positive, and positive divided by positive is going to be positive. If you plug in a number very close to either the far right or the far left endpoints, and you take that square root of 32 and you square it, you get 32. You multiply by 2, you get about 64, and then 32 minus the 64 is definitely going to be negative. Denominator is always positive, and so these over here are going to be negative. And so when is this function decreasing? It's decreasing from negative 4 square roots of 2 all the way to negative 4, and it's decreasing from 4 all the way to 4 square roots of 2. That's when this function is decreasing. They want us to give us a reason for our answer. And again, we analyze the derivative. We found out where the value of the derivative was less than 0, and we want to basically write that out. And we're going to say y prime, which is our derivative, was less than 0 on these intervals. Your guys' turn. Try the next one. Find the intervals when this function is decreasing, and then give a reason for your answer. Welcome back. In order to find decreasing, we got to find where our derivative is negative. This function over here is y is equal to x plus 4 times x to the negative 1 power. So we're going to get 1 minus 4 x to the negative 2 power. This derivative over here is going to be this 1 minus 4 over x squared. The question is, does this ever equal to 0, and is this ever undefined? So if we set that equal to 0 and solve, multiplying both sides by your common denominator gives us this x squared minus 4. This is equal to 0, meaning that x squared is equal to 2, and x is equal to plus or minus 2. Additionally, this function is undefined at x is equal to 0. That point x equals 0 is a point that's not in the domain, and so we really got to deal with that as well. And so we go look over here at our interval. We have critical points at negative 2 and positive 2. We have another point at 0. This point over here happens to be a vertical asymptote. My denominator is going to 0. My numerator is a non-zero number. And you're going to get unbounded behavior there. We got to figure out what's happening to our derivative on each of these intervals. And so when I look at this point, I got to identify what's happening at each of these intervals. And again, plug in some points. If you plug in a large magnitude negative number, the 4 over x squared will be very small, very close to 0, and 1 minus that is going to be positive. If you plug in a number between negative 2 and 0, like 1, you're going to get 1 minus 4, and that's going to be negative. If you plug in a number between 0 and 2, like 1, you're also going to get negative 3, and that's going to be negative. If you plug in a large positive number like 1,000, it's going to be very close to 1, which is going to be a positive number. And so what are the intervals where this particular function is decreasing? It's going to be negative 2 to 0 and 0 to 2. What is our justification for this? Y prime is going to be less than 0 on these intervals. Again, when is a function increasing? When the derivative of the function is positive. When is a function decreasing? When the derivative of the function is negative. Hope our lesson made sense, and I will see you guys next class period.